This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, all right, the system is recording. I think we should get started. So this is the last lecture of the potential flow part. And I'm going to give you some review of what we have done for the potential flow part of the subject. It is very nice of Leon that he decided to show you some of the solutions of assignment 1. It's just some figures, but I think if what you got from your code looks very different from these examples I'm going to show you, probably you want to have a look at your code again. So this is how it looks like for Q1D. You should get something close to this. This one is just two point vortices at the prescribed locations. So it should be straightforward to get this one, I think. And this is how it should look like for Q2C. This question is for you to prove that one streamline looks exactly like a circle, which is shown by this. Let me zoom in, which is shown by the, you can see it, the green dashed line here. You should get something similar to this. And this is Q3B. The flow field looks like this. And this one is for the mixing particle problem. You start with a blob of dye, which looks like this, and then after mixing with some different parameters, you get a pattern like this. And this is case D, which is very well mixed, and this is case E. It looks less effective than case D. I think that's all he gave me. Okay, so now about the exam. I think this is what you're most worried about. So we're going to have a 3-hour exam at the end of semester, and the exam is a hurdle. The exam goes like this. We have half of the questions for potential flow, and the other half for compressible flow. So basically, we have for the potential flow part, we have 4 questions, but you are only required to answer 3 out of them. So distribute your time wisely. You don't have to answer them all, just 3, because we are going to calculate mark for the 3 questions in the end. For those cases, if you try 4 questions, I think what we did in previous years is we mark all of them, and we pick the highest 3 out of the 4 you attempt. I'm not sure what else to say about the exam. For the compressible flow, I think it's up to Professor Brown, but I think he'll follow this convention as well. Okay. I hope there are some Game of Thrones fans. Okay, so here's the serious part. Let me give you know that you can find all the past exam questions from the library. And just search the subject code MCEN 90008, and you should be able to find all the questions. This is just an example to show you how the exam looks like. For the potential flow part, we have 4 questions. See, you're clearly instruct that you should only answer 3 questions out of 4. And usually we have a question that is mostly about the derivation of equations. You probably see something similar to this, and then you're asked to simplify the equation or derive something out of this. So what I'm trying to say is that this part is really closely follows the lecture slides and lecture notes. So make sure you're comfortable with all the derivations. This is just to simplify the Navier-Stokes equation and get Helmholtz equation out of it. That's question 1. And for question 2, you have you have some basic flows and show this relationship between velocity and the stream functions. This should be, well, as you can see, although it is a big, it seems to be a difficult question as a whole, but we always break it down into small parts and give you, and use these baby steps to guide you through them. So just don't panic. You can find this, and the next one is another complex potential question, and the last one is about Joukowsky transformation. So just be prepared of whatever is covered in the lecture should show up in the exam. Okay, so so for the lecture today, I'll probably solve 1 or 2 questions and show you the workings. I'd like to start with this one because it's very close to what we have covered in the past 2 lectures this week. So this one is about the Joukowsky transformation. You can find it as question A4 in the 2014 exam, but I'll just copy and paste the question here. Okay, so part A, we have a flow over an airfoil, and we know it can be modeled using conformal transforms. Why are the conformal transforms used in potential flow theory as opposed to non-conformal transforms? This has been covered in lectures. Any ideas how to answer this? It's just a 1-mark question, so the answer should be just like 1 sentence. So why do we prefer conformal transformations over non-conformal ones? Can you speak louder? I cannot hear you. Just. Okay, so conformal transformation means that the angles is preserved through the transformation. And what is related to angles? In the original plane, we have constant lines of stream function and constant lines of potential function, which are perpendicular to each other, means the angle between them are 90 degrees. And this property is preserved through transformation, which means that if a solution satisfies the governing equation, which is basically the Laplacian equation in the original plane, then after transformation, this property should also be satisfied in the new plane. So to put it this way, you have a flow in the original plane, and after transformation, you can be certain that it is still a fluid flow. It is still a potential flow. I just took this one from lecture 15, but you can always write it in your own words, okay? So this is part A. It's just a bit of warm-up. Let's have a look at the next one. You have been given a figure like this. It's just a sketch of the transformed plane after applying a rotation and Budley shift transformation to the flow over a rotating cylinder. And you have been given the radius of the Joukowsky circle, which is the red circle. And the radius of the black circle is A, equals to 1. And here we have to determine the horizontal offset, x0, if the vertical offset y0 is given as 0.2. So let me show you. I really want to have only one screen for the document camera. But can you remember this in your mind? Okay. Maybe I should just sketch it. So I'll just reproduce that figure here. We have a Joukowsky circle. And and we have another big circle that has been transformed through a rotation and a Bartley shift. So the center of that big circle has been changed to this point rather than the origin. And then just let me draw the circle around it. Okay, so the radius of this circle is A, and the radius of the Joukowski circle is C. And I'm going to define this as y naught and this as x naught. So what we know so far is that A equals to 1 and C equals to 0.9 and y naught is 0.2. And we want to find what x naught is. Okay? So this is just a cambered airfoil, a transformation to get a cambered airfoil, right? If you still remember what happened yesterday. So to solve this, we just have to connect this point, the critical point, with the center of the big circle, and then just take this triangle out of it. Here is 90 degrees. So we can apply the Pythagoras theorem, and we know that this length is A. So A squared equals to, here is y naught, plus this length is C plus x naught squared, right? So we can just solve this to get x naught equals to, we move y naught to the left-hand side of the equation, A squared minus y naught squared minus C, okay? And all these numbers have been given. So A equals to 1, C equals to 2.9, and y naught equals to 2.2. We can plug all of this in. And what I calculated yesterday was I got 0.08 after substituting all the numbers into this equation. Okay? Sorry. All right, I'm going to switch the screen back to the slides. This is the proper version of the sketch. That green triangle I was looking at is just this triangle here. It just helps you. Sorry. And then another part of the question is this shape of the airfoil in the transformed plane symmetric? Is it? No. No. Yeah, that's right. Because it's a cambered airfoil, so it's not symmetric anymore. Okay, that's question B. And so far we got 3 marks already out of 10. We're doing well, right? Okay, now part C. A slightly more challenge. Okay, let me read this out for you. The location of the stagnation point on the surface of a rotating cylinder is determined by this equation. So you don't have to memorize this equation. And given that the circulation required to satisfy the Coulter condition is given by this, and we need to determine the angle of attack alpha in degrees of the flow of an airfoil. I just made this sketch yesterday. Hopefully, I don't know if this is easier for you to understand compared to the to my handwritten sketch. But what I'm trying to say is that, so when you look at this, I'm just trying to show the relation between these angles. We have the incoming uniform flow. we have the incoming uniform flow rotated by angle of attack alpha. Okay, so this green line should be, if there's no angle of attack, this green line should be horizontal, right? But after applying this angle of attack alpha, it has been rotated by this much. So this angle of rotation is just alpha, which is shown here. And another angle here is beta, and that is related to the geometry of the airfoil, which can be determined by looking at this small blue triangle. Okay? So we have angle alpha and angle beta, and angle theta is the amount that we have to move the stagnation point by so that we can move the stagnation point back to the critical point. Okay? So that's the meaning of these three angles. And now we know beta because we know the geometry of the airfoil, and we know theta as given by this equation. So we just have to solve for alpha this way. The difference between this question and what we have done in the lectures is that usually we know angle beta and we know angle alpha, and we want to calculate the circulation. But here, we know the circulation already, so we just want to reverse the process and calculate the angle of attack. Okay, so let me switch to the document camera again. So for part B, we want to calculate theta, right? Sorry, no, we want to calculate alpha. What we have known so far is theta from that equation given to us. Theta is arc sine minus gamma divided by 4 pi u infinity times a. And we also know the circulation given to us in the question is 1.787 u infinity pi a. So to get theta, we can plug gamma into this equation. So we get theta equals to arc sine. Substitute that into this equation. We got negative 1.787 u pi a divided by 4 pi u infinity a. So this can be cancelled out. And we find that theta is minus 26.54 degrees according to my calculation. Feel free to check the math. Okay, so now we have theta, and we also know there's a relation between theta and alpha and beta, which is theta equals to minus alpha plus beta, right? So in order to calculate alpha, we know theta already, and we also need to compute beta before we can calculate alpha. So beta, let me remind you of that triangle we have been looking at. The blue or the green triangle is like this. This angle, the tip, is defined to be beta. And we know that this is A, and this is Y naught. So, which means we can have sine beta equals to Y naught divided by A. So we have beta equals to arc sine Y naught upon A. And that is found to be 11.54 degrees, according to my calculation. Okay, so now we can put everything together. We have calculated theta here, and we have beta here. So in this way, alpha would just be minus beta minus theta. And that gives me around 15 degrees. Okay. Any questions? Yeah?
Can you please go over what the significance of alpha and beta was again?
Okay, sure. Maybe I'll just switch to the slides. Okay, at least one screen, maybe both. Okay. So when you look at this line, the green line, that shows the direction of the incoming velocity, and you rotate it by a degree of alpha. That's the angle of attack. Okay. So if there's 0 angle of attack, this green line should just be horizontal. But because of the angle of attack, it has been rotated, and this angle is just alpha. And beta is something related to the camber of the airfoil. So for a symmetric airfoil, there's no beta at all. But for the cambered airfoil, since it's not symmetrical anymore, and which means that even if there's no angle of attack, the airfoil can still generate lift, which means that when there's no angle of attack, the airfoil can, the stagnation point is still not at the critical point. So we need to rotate that amount to account for this geometry property. So beta is just this small angle. See, that's directly related to y naught, which is which can be used to calculate the camber of the airfoil. So this is beta. And theta is just the total amount of the stagnation point that has to be moved for it to go back to the critical point. Any other questions? Oh, okay, that's just about the definition of theta. So if you look at this figure, you probably want to say theta equals to positive alpha plus beta, right? But the thing is, the way we define theta in a cylinder with circulation is that this is a cylinder, and we have the flow coming this way. So if there is a positive circulation, let's say positive circulation means it's rotating counterclockwise. Okay, and the two stagnation points would be moved downward. So these are the two new stagnation points moved from here to here. And the angle, if we look at this one on the right, this is usually how we define theta. So when theta is going clockwise, that means it's a negative number, and that's where that negative sign is coming from. It's just about definition, but you're right. If you look at the figure, theta equals to positive alpha plus beta, but there's a bit of history behind it. Okay, very good questions. Anything else? All right, so here we got another 3 marks. How much we got in total? 6, I think. We can pass now without answering the following 2 questions. Okay, let's have a look at the next question. So we have the velocity in the transformed plane given by this equation, and okay, so the question is, we can show that dz4 upon dz can be expressed as this one. And just to help you a little bit, all these 4 steps of transformation we need are actually given in the exam paper, so you don't have to worry too much about it, okay? You can see the exam is really helpful to some extent. Okay, let me show you how to do this. But this is really similar to what we did in the lecture as well, so it's a really a great idea to make sure you understand everything from the lecture notes. Okay, so what we need to find here, we want to find a relation between dz4 and dz. So we need to calculate this. We need to show that dz4 upon dz is y minus c squared z e I alpha plus x naught plus I y naught. That's good. So this is our goal. Okay, we want to get this. Okay, so we need the chain rule, right? To find dz4, dz, it can be written as dz4 upon dz3 times dz3 divided by dz2 and 2 by 1 and finally 1 by z. So we can break this one to these 4 parts, and each part can be calculated directly from that 4 steps. So let's go backward. dz4, dz3 is, let me remind you of the step, the transformation. So this z4, the last step, remember, is to rotate the flow back to horizontal. So z4 equals to z3 times e to the power of I alpha. There's no negative sign here because we want to reverse what we did in the first step. So in this case, the derivative is just e I alpha, right? And next one, dz3 upon dz2 is, this is the step of Joukowsky transformation. z3 is z2 plus c squared divided by z2. So differentiate that, we get 1 minus c squared upon z2 squared. Okay, and the same for the other two. dz2, dz1 is just another. This is the rotational or bodily shift. Yeah, that's the bodily shift. Sorry, I forgot. So it's just 1. And finally, dz1, dz is the first rotation, e to the power of minus I alpha. Okay? So now we have to put all of this together. So we can get dz4, dz equals to, this multiplied by that goes to 1. So all we really have left is just this one, 1 minus c squared divided by z2 squared. Okay? There's just one more step from here to our final solution, and that is we don't want z2 in the final expression, so we're going to use these relations again to replace z2 by z. Okay? So remember this, z2 equals to z1 plus x naught plus I y naught. This is the bodily shift, and we can substitute that to this equation. We got 1 minus c squared z1 plus x naught plus I y naught. But here I want to say that I don't want z1 either. I need to get rid of that and put z in the equation. So similarly, z1 equals to z times ei alpha minus. This is the rotation, the first rotation we applied to the flow. So we substitute that to this equation. We got 1 minus z e minus I alpha x naught plus I y naught. Okay, all done. Oh, sorry. Any questions about that? No? Okay. So just another 3 marks. Okay, so here's one more question to finish it up. It's just a 1 mark question. And this is about, due to the assumptions made in the simplification of the NS equation, potential flow theory is only a good predictor in simulating a flow over an airfoil if certain flow and airfoil conditions are met. So this is about the limitations of this method, which was covered yesterday, right? And we were only asked to list 2 of these conditions. So this seems okay, not very challenging. I don't know why it doesn't show up. Okay, so these are the okay. Please. Please, come on. Okay, here we go. So, sorry for the interruption. The answer to this question is you can just pick any 2 out of these things we just listed down here. So for the flow point of view, we have these assumptions such as 2-dimensional or inviscid or irrotational flow, and it is also limited to subsonic flows. So that's for the flow part. And in terms of the limitation of airfoils, it's only applied to small thickness to chord ratio or low angle of attack. Remember those 2 videos about separation we watched yesterday? That's the limitation to airfoils.
Incombustible?
Yeah. Yeah, that's also part of the flow. Yeah, I forgot to list it. Thanks. Okay, so it's all done, and we got 10 marks out of 10 for this question. Okay, so this is another question. If you're ready to move on to a new question, I think I heard some voice yesterday that we want to see how to sketch a flow field, and you want a really, really hard one. So I went back to my office yesterday and searched through the past exam questions, and I couldn't really find a hard one. I don't want to make you feel bad about it, but I really tried, and I just find this one might be a good example, although it's not asking me to sketch a flow field. But I think it's a good example to to familiarize you with some of the techniques that I normally use. I always get this, I have been tutoring this subject for like 3 years at least. And every year, one question that I keep getting is how to sketch the flow field. You make it so easy in tutorial because you have the solution with you, so you know how to sketch it. But what if you're asked to do the sketch in an exam? What should I do? So I really don't have any, one for all solution for that. I just don't know how to explain it. There are certain techniques you can use, but I'm not saying they're applied to all flow fields. So it all comes down to your practice and your understanding of how you expect the flow to behave, something like that. Yeah, that's the best I can explain. But okay, so now let's have a look at the question. Part A is just a warm up again. We have a source defined as a constant volume flow rate emerging from a point and flowing along the radius direction. And we have this relation between velocity components and the stream function. We have to make use of the conservation of mass to show the stream function can be written as this. Okay, I'm pretty sure this has been covered in tutorials, but just let me do it again. Okay, so for the flow of a source, this is the center of the source, okay, and we have the flow coming out of it, like this. And the conservation of mass means that the volume, if you draw a circle around it, okay, no matter what the radius of the circle is, whether you draw a circle here or you draw a larger circle, as long as these circles are centered at this point, then the volume of the flow passing through each circle along the radius direction should be a constant. So, which means that we can use that property to calculate the velocity of this flow. We know there's only one component, u theta, the flow going around it, along the azimuthal direction is 0. Okay, there's no flow going around the circle, so all of them are just going this way. So we can write it as the volume. If I take this circle as an example and I say the radius is r, so the integral of the velocity around this circle should be ur multiplied by 2 pi r, right? Because we assume that it is symmetric, so ur is the same along at all points. And this should equal to that volume q, which has been given to us. So we can find that ur is equal to q divided by 2 pi r. And now here's the time to use the relation between velocity components and the stream function, which is ur is 1 upon, okay, I need to check. 1 upon r d psi d theta, right? We can use this relation. So we know that ur is q upon 2 pi r. And in order to calculate psi, we just have to move r to the left-hand side of the equation and then integrate it. So we can write d psi d theta is q divided by 2 pi r. It's a constant. So after integrating this expression, we got the stream function as q 2 pi times theta. This is q, this is theta. Okay, so that's question 1. And if you want to write it in the Cartesian coordinate, it's just q upon 2 pi arc tangent y divided by x. Okay, so far so good. I'll switch to the laptop again. Okay, that's part A. We got 2 marks. And here's the tricky part. They have a flow field set up like this. We have a sink and a source, and both of them have the same strength of Q. And then we have a uniform flow coming from left to right, superimposed on it. So we have to, this is the case where we have to look at the relative strength of the uniform flow and the sink and source to determine where the stagnation points are. Okay. As the strength of the sink and source growing stronger and stronger, it might affect on which axis you can find the stagnation points. I'll show you what I mean through the derivation later on. But for this question, we just have to show that at this case, which means the strength of the sink and source is relatively weak. You can say it's relatively weak, and the stagnation points are on the x-axis. It's just one case. But I want to use this one to show you how to analyze the flow in general. Okay, so let me switch to the document camera. All right, I'll just put a sketch here to remind you what's happening. We have uniform flow. This is the x-axis. This is the y-axis. And there's a sink. There's a source. The strength is minus Q, and this one's positive Q. And the distance is a small s. Okay? So this is the flow. And what we usually do for this kind of question is we superimpose the elementary components of the stream function to find the total stream function. So let's do that. The total stream function is, first of all, we have a uniform flow, which is just u infinity times y, right? And for the sink is minus q divided by 2 pi arc tangent y upon x plus s. So there are 2 things to be careful about here. First is the sign. We're looking at the sink, so we have a negative sign in front of the expression. And another one is the location, the center of the sink. It's not at the origin of the coordinate anymore. It has been shifted by this amount s to the left. So we have to reflect that in the expression as well. We can have another stream function for the source, arc tangent y x minus s. Right, so this is the total stream function. And the next step is to calculate the 2 velocity components, u and v. So let's do that. U equals to partial psi, partial y. Differentiate this thing by y, which gives me u infinity from the first term and the second term. Just to remind you, when you differentiate this guy, let's say the arc tangent x dx, okay? That equals to 1 upon 1 plus x squared. X is whatever inside this arctangent function. So for this one, we have q divided by 2 pi, 1 plus y x plus s squared. But that is not enough. We're differentiating with regards to y, so we have to apply the chain rule as well, which gives me 1 upon x plus s multiplied to the whole thing. Does it make sense? And we follow the same logic for the source term. We have 1 plus y x minus s and 1 x minus s here on top. Okay, so now we can simplify things a little bit. For the sink, we can multiply x plus s squared, both here and here. X plus s plus y squared. And q divided by 2 pi x minus s, just to make things look nice. Okay, it's getting trickier if you want to simplify this furthermore. So let's just leave it here for now, okay? And I want to have a look at the y component first. So for the v velocity, it equals to negative partial psi partial x. You really have to be careful with all these calculations. Just be patient. You should be able to get there. Okay, so differentiate that with regard to x. The first term goes to 0, okay? And the second term, I don't forget the negative sign, minus q 2 pi, and differentiate that, 1 plus yx plus s squared. And now I have to use the chain rule for this term, y upon x plus s as well. So I got y upon x plus s squared, and I have a negative sign in front of it. Okay? So this is the sink, and for the source, some similar steps. 1 plus y x minus s squared minus y x minus s squared. And this can be simplified to I'll leave this negative sign out. And for the first term, it goes to q divided by 2 pi. And this negative sign, this one cancels out. And again, I'm multiplying x plus s squared. So I got y upon x plus s squared plus y squared plus q, this should be minus q divided by 2 pi y x minus s squared plus y squared. Okay? And then I can pull y out. And then this whole thing can be simplified as qy divided by 2 pi times 4xs like this. So, which means that when we want to find the stagnation point, we need to have both u and v component as 0. And if we want to have v component equals to 0, that will give me either x equals to 0 or y equals to 0, right? Because I have x here and y here. So let's consider this condition. So just to remind you, this part of the question wants to have the stagnation point occurring at y. So let's take this for now. We can have y equals to 0 and plug it into the u component, okay? And in that way, u equals to 0 with y equals to 0, and we can solve for x. And x equals to plus or minus s y minus q u infinity pi s. The solution is that, which means that for this solution to be real, this parameter q upon u infinity pi s has to be smaller than 1. Otherwise, you'll get an imaginary number, and it's not going to work that way. Okay. Okay, so since I'm running out of time a little bit, I'll just jump to the MATLAB part. I really want to show you. I prepared this code for you, just to. Okay. Okay, so this shows that as this parameter changes its value, how the two stagnation points are going to move and how the flow field are going to evolve with that. So this is the case. This is the case when the parameter is smaller than 1, and that's not the case we want to look at. Sorry. Okay, so this is a nice case. When this parameter is larger than 1, okay, that's what we just derived. We have two stagnation points shown by the two red dots, if you can see it. They're sitting on the x-axis, and this is how the separatrix looks like, the red lines. And the blue lines, I'm just showing other streamlines. So one way to think about it is at this point, if you can calculate the velocity direction at the origin. And in this case, I calculate the velocity at the origin, and that's pointing to the right, which is the same direction as the uniform flow. So in that case, the flow here is going to the right, and just imagine you have a streamline coming out of the source, and in the beginning it wants to go left, but at some point the strength of the source is not strong enough to fight against the free stream, so it has to fold back at some point, and that kind of explains how you got this shape of the separatrix is folding back, right? I hope this is convincing enough for you to accept this flow pattern. But once the strength of Q has been increased to this, for example, the two stagnation points are moved onto y-axis. So the sink and the source are getting stronger and stronger, and it takes longer for them to travel to the for a particle to go out of the source to travel before it is forced to turn back by the free stream. Okay, so sorry I'm running out of time, but I think this is the general thinking of what I usually have when I want to sketch a flow field, especially when there's a parameter that is changing. And I try to see how the flow field evolves from one case to another case, and that usually helps me with sketching. Okay, so I think that's all I want to say. And in terms of preparing for the exam, go through the lecture notes and go through the lecture slides, and then the tutorial questions. We'll probably release the tutorial solutions after all the tutorial sessions are finished this week, so you can find them on LMS and study the tutorial solutions. So yeah, I think that's about it for the potential flow part. Wish you all the best.